All right, welcome to Pre-Calculus. We will be starting the year here with this prerequisite chapter, an overview of the topics, and I did put in here that you could highlight these as we go through them this semester. Also make a note of any that you think you might need some extra review on. So first property, just looking at some basic properties of real numbers. We will be looking at absolute value, distance and midpoint formulas, equations for circles, slope and equations for lines, applications involving linear equations, and we'll also look at solving equations and inequalities both algebraically and with graphing. For this first section, we will spend a couple days on it. Our first day will cover the first two objectives here, identifying subsets of real number systems and correctly using what we call set builder and interval notation. Those may be new to you. On day 2, we'll look at correctly using basic properties of algebra, using the properties of exponents, simplifying algebraic expressions, and going back and forth between scientific and decimal form. All right, so our first topic, looking at subsets of real numbers. This illustration hopefully clarifies how we build our subsets and what is contained in each one. The smallest subset here is the natural numbers. We usually use an n for that. And these are our basic counting numbers like 1, 2, 3, etc. If we go a little bit beyond that, if we actually add in the number 0, now we are looking at the set of whole numbers. We use a w for that. If we start adding in positive and negative numbers to that, such as -3, -2, -1, all right, now it is including 0 and our counting numbers here, since the box around integers contains the other two as well. So our integers are all our positive and negative counting numbers. We use a z for this, which can get a little confusing. So I want you to think of it as zintegers to help you remember that z represents the set of integers. All right, moving a little further out, we have what we call rational numbers. We use the letter Q for that. These would be numbers that can be written as a ratio, all right, or a fraction. So things like 1/2, -2/3 would be examples of rational numbers. All right, any decimal that ends or has a repeating decimal. For example, the -2/3 would be -0.6 repeating. The 1/2 is a 0.5, it's a terminating decimal. Now there's a break here. So we have all of these numbers to the left that are within the rational set, and then to the right we have the irrationals. All right, we use an I for irrationals. All right, these would be the non-repeating decimals, all right, and the non-terminating. All right, that means things like pi or the square root of 2. All right, you can check on your calculator. They do not end, they do not repeat. Okay, all of those are what we call real numbers. So we're going to be focusing for the most part this year on the real numbers. We can go beyond that and include imaginary numbers, which you should have worked with last year, such as positive and -3i. But that is separate from the real numbers. If we combine real and imaginary, we get this overall umbrella called the complex numbers. But for the most part, unless specified, we will be working with real numbers this semester. All right, sets that are contained within other sets are called subsets. All right, we've just been talking about all the different subsets of the real numbers. And this is the symbol for subsets. So we could look at this illustration and say natural numbers are a subset of the whole numbers, and whole numbers are subsets of integers. All right, using our symbols up there, we have the natural numbers, subsets of wholes, which are subsets of the integers, which are subsets of the rational, which are subsets of the real numbers, which are subsets of complex numbers. All right, two sets that have nothing in common are called disjoint or mutually exclusive. For example, rational and irrational. All right, they do not overlap. Real numbers and imaginary numbers do not overlap. Okay. And as we go through the video, make sure you do pause it if there's anything that you need to go back and relook at or just catch up on your writing. All right, at this point, pause it and grab your calculator. We're going to have you just typing a couple things in to see how your calculator shows you your answer. The first one is to just type in 7 divided by 4. All right, this is a terminating decimal. You should be getting 1.75 on your calculator. Okay. If you type in your calculator 4 divided by 11, you should see 0.363636 repeating. All right, so this is a repeating decimal. And then if you type in the square root of 3, you get 1.732050808, etc. All right, in this course, we typically take things out to the third decimal place. So I would write this as approximately 1.732. But it is a non-terminating decimal, so it is an irrational number. And it is infinitely non-repeating as well. All right, we approximate real numbers with the calculator. Remember that calculator response is not always exact. So if I ask you for the square root of 3 and you abbreviate it as 1.732 in your calculations, you might get a slightly different answer since you've done an approximation. All right, for the most part, we are trying to work as much as possible with exact answers. All right, so just take a second, pause the video and work through example 1 here, looking at the different forms. All right, just to double check. All right, if you type in 1/16, you should get 0.0625, which is a terminating decimal. If you type in 55/27, you do get a repeating decimal. And if you type in 1/17, you get an unending, non-repeating, non-terminating decimal. All right, the real numbers and the points of a line can be matched 1-to-1 to form a real number line. We start with a horizontal line and we match the real number 0 with the point O for origin. All the positive numbers are assigned to the right of the origin and the negative ones to the left. You guys have been working with number lines quite a bit, I'm sure. All right. But how many real numbers are between 0 and 1 on the number line? All right, we could take a number line and start dividing it. If this is 0 and this is 1, this would be 1/2. But then we could divide it again. This could be 1/4. All right, and each time you could keep dividing it. So there are infinitely many numbers between 0 and 1. Okay, the number we associate with that point is called the coordinate of the point. And since the set of real numbers is ordered, we can actually organize them on a number line. We can use inequalities to compare them. So given any two real numbers, one option is that A is bigger or greater than B. If that is the case, then A minus B is a positive number. Or A could be less than B, where A minus B is negative. Our other two options is where we include the equal sign, and that just means that we might add or subtract and end up with 0 if the two numbers are equal. So we will be using those inequality symbols when we compare numbers. We have a trichotomy property that says if A and B are two real numbers, exactly one of the following is true. Either A is smaller than B, A is equal to B, or A is greater than B. All right, only one of them can be true at any time. Inequalities can be used to describe intervals of real numbers. All right, so let's look at this example. Now there is something new in this one that you did not have in Algebra 2. If you were asked in Algebra 2 to describe and graph the interval of real numbers represented by this, we read this as x is less than 3. What you probably did is you started making a number line, All right, and you would have put an open circle at 3 and put an arrow to the left to say you want all the numbers that are smaller than 3. In pre-calc, we use a slightly different notation. We still need to have that 3 on the number line, and if you want to include other numbers on either side of it, that's fine. But the symbol that you're going to be seeing is, instead of an open circle, it's just a parenthesis. And then we still include the arrow to show which side we want to use. Okay? If we have a compound inequality statement, like in example B, this is read -1 is less than x, and x is less than or equal to 4. So again, in our old method, we would have had to have -1 and 4 on our number line. We would be shading for x's in between that. And in terms of our circles, since the -1 can't equal x, we would have that be an open circle. But since x could be 4, we'd have a filled in circle. Okay, shifting to our new notation, we still want to include the -1 and the 4 on our number line. But now we are going to do that rounded parenthesis in place of our open circle, and we're going to use a bracket or squared off type of parenthesis for a closed circle. And again, we want to shade everything in between. All right. For example 3, I'm going to give you a statement in words, and I want you to write an interval and then draw its graph that would represent it. So our first one, it says the real numbers between -4 and -0.5 or 1/2. So with an inequality statement, we always want to put the smaller number on the left. So we would say -4 is less than x, and x has to be less than -0.5. Okay. Using our graph, our new notation, both would have rounded brackets since we cannot equal those endpoints. And then we do include the endpoint numbers, the coordinates of those, and shade everything in between. So between typically does not refer to being equal to those endpoints. In example B, it says the real numbers greater than or equal to 0. So we would write x has to be greater than or equal to 0. And since it can equal 0, we would use a squared off bracket. And we want to shade everything to the right, where the numbers are greater. If you want to include other numbers on your number line, you certainly can. All right, some notation for sets. We can name it we can just give it a name, like set M. We can state our set by listing all the elements. For example, the set that contains the elements 1, 2, 3, and 4. Sometimes our set is very long, so we could list it showing a pattern and then include the ... just to mean that the pattern continues. All right, this is called the Fibonacci sequence, 1, 1, 2, 3, 5, 8. We can specify it, and this again is probably a new notation for us this year, using what we call set builder notation. It uses the same kind of brackets, but we read this as n such that, that's what our slant or our vertical bar here means, n such that n is less than 4. All right? Or we can put it in that interval notation where we use our brackets and our open parentheses to represent if it's included or not. All right, so let's look at a couple examples. In this case, we are looking at what we call bounded intervals, where there is an endpoint. It says let a and b be real numbers with a smaller than b. And again, we always put the smaller number on the left. In interval notation, if you see this, it means that a and b are both included. That's what the squared brackets. All right, so we have our graph here. In inequality notation, we would say a is less than or equal to x and x is less than or equal to b. We refer to this as closed since both endpoints have an exact cutoff. The next one down can get confusing because students sometimes think of it as an ordered pair, but you have to put it into the context. So if you are talking about interval notation or a set of numbers, this would not be an ordered pair. It would be an open interval where A and B are not included. And again, we use the rounded brackets in our graph. But we can also have a combination. In this first one, it is closed on the left, but open on the right. So squared off bracket here on the left, opener bracket on the right, rounded bracket. That's referred to as half open. And we can have it the other direction as well, where it's closed off on the right-hand side. Okay, and again, that's our inequality statement. A is less than X, but X is also less than or equal to B. Again, that is referred to as half open. But in both cases, they are bounded because there are specific endpoints stated. All right, so question. Describe the interval of real numbers determined by the inequality X is less than 2. All right, so we want all the numbers smaller than 2. On a number line, we would look at it like this. Okay, rounded bracket at 2 and everything included to the left of that. That means it's going towards negative infinity. So if we were going to state this as an interval, we could say from negative infinity up to 2. We still use rounded bracket because we can't equal 2 and you can never actually reach infinity. So infinity always has that rounded bracket around it. And in this case, it is unbounded because we do have that infinity. There is no bound to infinity. And since it does not contain 2 as its endpoint, we say that it is open. The interval notation from negative infinity to infinity represents all real numbers, the whole set. So looking at a few unbounded ones. Again, unbounded means it has infinity. Infinity or negative infinity could be. Okay, so in this first one, we are looking at the interval that starts at A, including A, and goes to positive infinity. So it is going off to the right, but it has a closed bracket there. So we do refer to that as closed. Next one down, the only difference is that it is open. So it has a rounded bracket, meaning we get very close to A, but we don't actually get to A. The last two are bounded on the right instead. Let's try to move that up here. All right, first one is closed. Again, squared off bracket. This time we're going towards negative infinity on the left. And then the last one is open, rounded bracket, but still heading towards negative infinity. Okay, so open means the endpoint is not included. Closed means it is. Bounded means it does not involve infinity. Unbounded when it does. All right, example 4. Describe it as bounded or unbounded and open or closed. So our first one, since it has infinity in it, we would say it's unbounded. And there are no squared off brackets, so we say it is open. All right, pause the video for a minute and try B and C. All right, let's check what we got. On this one, it does include infinity, so again, it is unbounded. But this one is closed, since there is a squared off bracket there, using the endpoint 5 as its final spot. In example C, it does not involve infinity. It's all the numbers between 2 and 7, including them. So it is bounded and closed. All right. Couple things to caution you about when using interval notation. If the interval is open, I had mentioned this before, don't confuse it with being an ordered pair of numbers. Interval notation can only be used when talking about intervals of real numbers through continuum. All right, so there can't be a break in the numbers. And the last one, interval notation must be written from least to greatest. For example, we can use this symbol, but this one would be wrong since 9 is bigger than 4. All right, example 5. Draw a number line graph and write each in both set builder notation and interval notation. First one says all numbers greater than 4 and less than or equal to 9. So we want numbers that are going to be bigger than 4, so 4 is our small end, but we want them to be less than or equal to 9. Okay, so less than or equal to 9 looks like that. X is less than or equal to 9. On the left-hand side, remember you have to read that as 4 is less than x, which means x, if we read from here, x is greater than 4. Okay? On a number line, we have 4 and 9 as our endpoints. We can include 9, so we would put a squared off bracket there. We do not include 4, so we would do a rounded bracket. And then we want to show that we want all the numbers in between there. All right, with interval notation, we just use the same brackets we put on the graph. So rounded at 4 and squared off at 9. Now, set builder notation. That was that one that I said earlier was probably new to you. We would say we want the set of numbers x such that, and then we bring that statement down. 4 is less than x, and x is less than or equal to 9. Okay, so this is called set builder. This is interval. Okay, second example. All numbers less than 4 or greater than or equal to 9. Okay, so let's think about that. We want numbers that are less than 4. On a number line, we would put 4 in, and we want numbers that are smaller than that. So we would have rounded bracket, and we want to shade that section. Or they can be greater than or equal to 9. So now we can include 9, but we can also be greater than it. Okay, so a graph would look like that. In terms of our interval notation, we're going to have to break this into two parts because there is a break in our number line, the part that we've shaded. So for the part on the left, we are starting here at negative infinity, and we are going up to 4. We can never get to negative infinity, so it's a rounded bracket. And according to our graph, we can't actually equal 4. We have to be smaller than it. Or, and we use a union symbol for or we can start at 9 and go towards positive infinity. Rounded brackets are always used at infinity. Okay? With set builder, we're going to say we want the set of numbers x such that x is less than 4 or x is greater than or equal to 9. All right, why don't you pause the video and try example C. All right, let's check our work. The set of all Fahrenheit temperatures for which water is in a liquid state. All right, water freezes at 32 degrees, so we need to be bigger than 32 degrees. And it turns into a gas at 212 degrees, so we have to be smaller than that. Okay, that's our interval. So on our number line, we need 32, we need 212, and we want to be everything in between there. Okay, set builder notation. And we don't have to use an x since we're talking about temperature. We could say T such that 32 is less than T and T is less than 212. All right. Example 6. Write each interval notation as an inequality and graph on the number line. The nice part about giving it an interval notation is your graph is going to look identical. We want to go from -6 with a square bracket up to +3 with a rounded bracket. We're just shading everything in between. So that's the easy part. Stating it as an inequality, same order. We have -6 and we have 3. We want x to be everything in between there. Since we cannot get to 3, we have to be smaller than it. We need x to be less than 3. And on the left side, we can actually hit that -6 mark, so we're going to use the less than or equal to. So again, reading from x, x is greater than or equal to -6, but less than 3. Okay, question B. It is unbounded. We're going all the way to -infinity over here. All right, we have a cutoff at -1. Okay, so in an inequality statement, we want all the values for x that are less than -1. Okay, for C and D, we're going to go the opposite. I've given you the inequality statement. I want you to put it in interval notation. Since both of these have equal signs here, we would use squared off brackets, and we just bring our numbers over in that same order. We want everything from -2 to 3, and the same thing with our number line. We want all values between -2 and 3. And the last one here, 4 is less than x, which is less than or equal to 9. Since there is no equal sign here, rounded bracket at 4, closed off bracket since we can equal 9, shading everything in between. And the same for our interval notation. All right, so the last page that we're going to look at today. There's a difference between and or. In set builder notation, if you say something like this, 20 is less than n and n is less than 60. That can be combined into a compound inequality since they are connected. So in that case, we are looking at less than or equal to symbols. We never want to turn that around where we put the smaller number on the right-hand side, whether we're putting it in set builder or interval notation. That would be a no-no. All right. The or is what is used if there is a break in your graph. So in set builder notation, we can say m such that m is less than or equal to -5. So everything to the left are equal to -5. Or we could have that break and jump to a +3, and we want m to be greater than or equal to 3. Okay, interval notation looks like this. The or is that union symbol. All right, so again, we do not want to put smaller numbers on the right-hand side. Okay, so just be careful how you're organizing your numbers. Example 7, write in both set builder and interval notation. The set of all n that are less than 3 and greater than or equal to 7. Well, if you think of a number line, here's 3, here's 7. Can we be over here, less than 3, and at the same time be greater than or equal to 7 over here? We can't be in both places at once. That would be an or statement. So since they're asking for the and or the overlap or intersection, all right, there isn't one. Okay, so we can use the symbol, a 0 with a slash through it, or we can use empty set brackets, right, to say we have the set of no numbers. Part B, the set of all x's between -6 and -15 inclusive. Inclusive means including those numbers. Okay, now if you think about a number line, -15 is over here, -6 is over there. So if we're putting this with smallest number on the left, we would say from -15 to -6. Inclusive would be squared off brackets. Set builder notation, all x's such that negative 15 is less than or equal to x, and x is less than or equal to negative 6. Oops, that should be a set bracket. All right, and our last example for today. Express the following number line graphs in both set builder and interval notation. Now you'll notice that there's several pieces here, so we're going to have to take each one separately. Our first chunk is right in here. We want to go from negative 3 to negative 2. Since we have a solid dot, it means it includes negative 3, but it does not include negative 2. Then there's a break, all right? There's no solid dot there. Or we can be in this section, okay, where we start just above negative 2 and we go up to 0, including it. Or, let me get a different color here. Or we could start just above 1 and keep going all the way to positive infinity. Okay, so that would be the interval notation for that. Set builder notation. X such that, now our first one, we say negative 3 is less than or equal to x, and x is less than negative 2. Or negative 2 is less than x, and x is less than or equal to 0. Or x has to be bigger than 1. Okay, so pause the video for a minute and try the last example here. All right, so let's check your work. In interval notation, you should have a rounded bracket from negative infinity to negative 4, squared off bracket. Or from negative 3 to negative 2, including the negative 3, so squared bracket, but not including negative 2. Or, now this one's a little tricky because of just that solid dot there, it's just the number 1. We do not use the rounded or squared off brackets because that represents an interval of numbers, and we just have a single number, so single set. Or we can go from 0 to 2, not including 0, but including a 2. And then our set builder notation. Here we want x to be less than or equal to negative 4, or negative 3 is less than or equal to x, less than negative 2, or x could be 1. Sorry, that should be a negative 1. Or 0 could be less than x, and x is less than or equal to a positive 2.